Hi, welcome to this video showing you how to simulate Brownian motion. All you need is access to Python. First thing to note is that Brownian motion is normally distributed with mean 0 and variance t. The probability density looks like this. So this is very similar to the probability density function of a standard normal with mean 0 and variance 1, except this time you see a t in the exponent here, and also a t multiplying the 2 pi on the outside. The shape of the distribution is a kind of bell shape, and it's symmetrical about 0. 50% of the data is to the left, and 50% is to the right. Okay, so now we want to simulate these normal random variables. In Python, it's very easy to simulate uniform random variables between 0 and 1. So these will give you a number between 0 and 1 with equal probability, right? Any value between 0 and 1 is equally likely. And from that, we can transform them to normal random variables using this inverse cumulative normal function. So this is very similar to the standard cumulative normal function, which takes you from some value of x to a probability. So it says, given a value of x, what is the probability that a standard normal is less than that value of x? Right? This goes the other way around. So we're simulating these uniform random variables, so they're numbers between 0 and 1, and it turns it into a value of x. Here's an example in the diagram. So the area here up to x is u0. We're integrating from minus infinity to x0. Right, so this just takes you from u0 to x0. Let's take a concrete example with some numbers. Okay. So here suppose we simulated this uniform value and we got 0.9871. This inverse cumulative normal function would return 2.231. Let's take another example. Okay, so this time, suppose we simulated and got 0.8176. This inverse cumulative normal function would return 0.906, right, which is the value you have to integrate to, such that the area under the curve up to that value is 0.8176. There's another one. Okay, this time the probability is less than half, right, which means your x has to be negative, right? So if your probability is more than half, your x will be positive on this side. If your probability is less than half, your x has to be negative. And we get minus 0.153. Okay, this time we're just slightly positive. We'll do another one. Okay, well here we're slightly positive again, very slightly. So the probability is 0.5374, and we plug it into this inverse cumulative normal and we get 0.094.
Okay, now we're going to use Python. We'll use NumPy to generate the uniformly distributed random numbers and the function ndtri for the inverse cumulative normal function. Okay, firstly we're going to use the default random number generator. And once we've created that, we'll use the function random to generate 10 uniformly distributed random numbers between 0 and 1. Right, we'll print them out. Okay, now we're going to demonstrate the function to calculate the inverse normal distribution. We'll try it out on 3 probabilities. These are quite common ones: a half, 95th percentile, and 97.5th percentile. You probably know the answers to this already. We'll use the function NDTRI and round off the answer to 3 decimal places. Okay, let's run the program. Okay, you can see we've got an array of 10 random numbers between 0 and 1. Don't quite fit on the screen, but you can see them. And then after that, we've got the probabilities and the corresponding x values. So 0, 1.645 and 1.96. Now we have learnt how to simulate uniform random variables between 0 and 1 in Python, and also how to transform them into normal random variables. So let's simulate 5,000 normal random variables, create a histogram, and compare this with the theoretical distribution of values. We would expect them to be quite close. We are shooting the simulated points from a gun, and they are being added to the number line, and the histogram is being constructed under the theoretical frequency in the top right. We speed things up a bit. As you can see, the values are quite close. Finally, we want to create a path of Brownian motion. To do this, we divide the simulation time into a number of time steps. We multiply each normal random variable by the square root of the time step and sum up to get the path. Let's look at some examples of simulated Brownian motion for 1 year with 100 time steps.